Hello, this is Mr. Kingsbury. Welcome to the Finding Inverses notes. So we're starting a new unit with these notes, a new unit on inverses and composition, I guess. Don't forget to put your period and the date. Very important. Today's essential question is, what is an inverse? And how do I find one, that should say one, graphically, tabularly, and algebraically? And just so that you guys understand what I mean, graphically means how do I find one on a graph? Tabularly means how could I find one if I was given a table? And then algebraically, of course, is with an equation. That's going to be the last one that we do there. In fact, what I'd like to do is define it first, and then let me show you some examples. The first few are pretty straightforward. We'll do graphically second to last, and then algebraically the last, I guess. Excuse me. So what is an inverse? Essentially, an inverse, maybe we call it an inverse operation. We'll just call it the inverse. An inverse operation, let's call it an operation. Inverse operation undoes another operation. So, for example, the inverse of multiplication is division. The inverse of adding is subtracting. And it gets more complex from there, but it's basically undoing what you've done. Think of it in terms of finding a new location around town. Like, let's say you meet a new friend and you're going to their house for the first time. So you have directions to get there. I realize we all have cell phones, but even on the cell phone, it's telling you, go so far for a quarter of a mile, then turn right onto this street, then go for a mile, then turn left onto this other street. Well, when you go back, it's undoing all of those. Everywhere you turned right, you now turn left. Everywhere you went left, you now turn right. If you're going east, now you're going west, and so forth. That's what an inverse does. So why is that important? Well, sometimes we need to undo what's been done. More to the point, inverses are very important in solving. That's how we kind of figure out what the value is that we're looking for, is we use inverse operations. So how do we identify if things are inverses? Well, it kind of depends on what you're looking at. Let's start with something simple like ordered pairs. Let's say that I give you the ordered pairs 1, 5, 7, 2, -6, -3, and -4, -9. So this is our function. The inverse is simply these ordered pairs, but we flip-flop the y and the x. So it'd be 5, 1, 2, 7, -3, -6, and -9, -4. All I did was flip-flop the x and y. So let's make a note here. Switch the x and y values. Easy peasy, lemon squeezy, as they say. My kid likes to say that. So that's pretty easy. And tables are pretty much the same. Right? So if I gave you a table with points on it, like let's do -2, -4, -1, -2, 0, 0, I don't know, 1, 2, 3, 6. That's pretty good. All right, so that's the function. Ooh, I probably should have called it that. We'll call this the function. Then the inverse would be all of these things, but we switch them. And I guess you could technically write this as y, x. I don't know. What you need to know is that the table's flip-flop. So this would be -4, -2, -2, -1. Ooh, 0, 0 looks exactly the same. That's important to know. All I'm doing is flip-flopping everything. That's all. Not a big deal. So we got that, ordered pair, tables. And what you'll be asked to do is find the inverse. Like we'll say, here's a table. What's the inverse table? Or what's the table of the inverse look like? And you'll just need to flip-flop those ordered pairs or those values on the table. Not a big deal. Next up, then we have our graph. This is where it gets more interesting. And I'll do the best that I can to show you what's going on. But I'm going to sketch it. So it's kind of rough. For a graph, it will be the inverse will be reflected. Inverse will be reflected over the line y equals x. So for starters, what does that look like? I'm just going to sketch a quick graph, and I apologize for its crudeness. But let's say we go 1, 2, 3, 4, 5. There's 5. 1, 2, 3, 4, 5. There's 5. 1, 2, 3, 4, 5. That would be negative 5. And 1, 2, 3, 4, 5. There's negative 5 again. The y equals x line is the line where all the ordered pairs have the same x and y values. So like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Negative 1, negative 1, and negative 2, negative 2, and negative 3, negative 3, etc. You see the pattern here. So it's this line right here. That's the y equals x line. Y equals x. So if you had a point, just a point, like say 3, 1, the inverse point would be 1, 3, which would be here. It's reflected over the line. And again, this is not a fabulous picture, but it's a reflection, right? They're reflected over this line. If I had, let's do something better. How about if I did the parent function y equals x squared? So that has the point 0, 0, 1, 1, and 2, 4, negative 1, 1, and then negative 2, 4. And it looks like this. It's just a bit of a sketch, right? That's my y equals x squared graph. If I reflected this over the y equals x line, so much like I did with my table and my ordered pairs, I'm switching the ordered pairs, right? So 0, 0 is going to stay the same. 1, 1 will probably stay the same, but look, 2, 4 will become 4, 2. And here's the fun one. Negative 1, 1 will become 1, negative 1. Negative 2, 4 will become 4, negative 2. So I end up with this. And we'll practice this in class, but essentially what it is you have taken your picture and reflected it over this diagonal line. Again, we'll practice in class, all right? Now the last one that I want to show you, and I'm going to do a couple examples of this, is algebraically. How do we handle that? And there's actually a kind of a process, I guess you would say, to it. Let me draw my little lines here. I did not get nearly as prepared as I thought that I did. Anyway, the process is simple, and I'll write this down. You switch the x and the y, and then you solve for y. So that's how you do it algebraically. And we're not going to give you terribly difficult ones. This can get kind of mind-numbingly complex if you want. We're not going to do that. Algebraically. Switch x and y variables to solve for y. So let me give you, I think I'm actually going to give you 3 examples. We're going to make the first one linear, the second one quadratic, and the third one cubic. I am going to say that with the last 2, I'm going to have to be kind of careful how I do it, but I think we'll be all right. So let's say we do y equals 4x plus 9. Step 1 would be to switch the x and the y variables, right? So that would make our equation x equals 4y plus 9. Ooh, of course I broke my pencil. Why not? Then we would solve for y. So we need y by itself. We would do that by subtracting 9. So we get x minus 9 equals 4 times y. And then we divide everything by 4 so that this cancels out. And some of you are going, well, what do you do here? I mean, you can leave it as x divided by 4 if you want. I like to put a 1 out there. That's just me. So we get 1 equals y, because 4 divided by 4 is 1, and 1 times y is y. So that would be the inverse function there. Let me do another one, example 2. What if we did y was equal to 5 times x squared minus 3? Once again, we would switch these. which would give us the equation x equals 5 times y squared minus 3. And then we're going to solve for y. So to do that, I'm going to add 3. That seems pretty straightforward, right? X plus 3 equals 5y squared. Then I'll divide everything by 5. Once again, I'm going to put a 1 in front of the x. I'm going to divide that by the 5. Remember, if your variable doesn't have a coefficient explicitly written out, it's assumed to be 1, right? So we have 1/5 x plus 3/5 equals y squared. 5 divided by 5 is 1. 1 times y squared is y squared. And now for the interesting part. Helps if you can see it, I guess. We need to undo this square. Well, to do that, you take the square root, and what you do to one side, you do to the other. So we would have the square root of 1/5 x plus 3/5 equals y. That would be the inverse function there. Pretty crazy, right? Let me do one more, this time with the cubic in it, just because you're going to see stuff like this on the test and in class, and I want to make sure that you see an example. Certainly, we'll practice it in class, and I'll make sure that there are lots of examples for you so that you have stuff to compare to. So here we go. You ready for this? I won't make it too hard, I promise. Example 3. Let's do y equals, how about 2x cubed divided by 7 minus 4. So once again, we'll switch the x and the y. That gives us x equals 2 times y cubed over 7 minus 4. And to be clear, this is y to the third power. This is 2 times y to the third power. This is division by 7 and subtraction by 4. So we need to undo that. We're going to start out here with this subtraction by 4. Let's add 4. So we get x plus 4 equals 2y cubed divided by 7. Next, then, we need to undo division by 7. And the opposite of that would be multiplying by 7. What you do to one side, you do to the other. So on the right side, this 7 and this 7, division by 7 and the multiplication by 7, they simplify to a 1. And 1 times 2y cubed is 2y cubed. On the other side, I'm going to have to actually distribute this 7. So I get 7x plus 28. So I'm at 7x plus 28 equals 2 times y cubed. Now I'm going to undo the times right here. So I'll divide everything by 2. So I get 7 halves x plus 14 equals, remember 2 divided by 2 is 1. 1 times y cubed is y cubed. And then last but not least, we must undo this cube. And to do that, you take the cube root, which starts out looking like a square root, but then you put a 3 right here. And what you do to one side, you do to the other. So when all is said and done, I will have the cube root of 7 halves x plus 14, and that will equal y. Remember, the cube root and the cube, they cancel out. So that would be my inverse. All right? That's really all there is to it. I don't think we'll give you anything more difficult than that. We'll practice in class, and I'll see you then.